call this class. Okay, hello, hello. Anyone has any questions? Good evening. Let me take a picture. See who's here on time. Good evening. All right, so we finished chapter 5 about sequence and series. So today we're going to talk about special series, power series. So power series has very close relationship with the functions. So we can look at some series from another point of view. We can look at some functions from another point of view, right? Because none of you are math majored. If you are math majored, you have to know this chapter very, very well. Okay, let's go. So we want to identify a power series and provide examples and determine the radius of convergence. So we have a new term today, right? Convergence. If we remember geometric series, right? Geometric series, if the ratio r less than 1, well, we see a convergence. It's a convergent series. So in that kind of ideas, so radius of convergence is saying, okay, in what interval, in what kind of condition the series converges, and the interval of convergence of power series, and use a power series to represent a function, right? Actually, use a convergent power series represent a function. Well, just use a power series, right? If a function is continuous, the power series converges at that point. So a power series is a type of series with terms involving a variable. More specifically, if the variable is x, then all the terms of the series involve powers of x. So think about a polynomial function, right? As a result, a power series can be thought of as an infinite polynomial. So power series are used to represent common functions and also to define new functions. So in this section, we define power series and show how to determine when a power series converges and when it diverges. And we also show how to represent certain functions using power series. Okay, so power series and the functions have some relationship. Okay, to form of a power series, again, with one variable, right? And each term is the variable x with a component. Let's see this one, a series of the form summation n goes from 0 to infinity. Okay, we used to let n go from 1 to infinity. So here we allow 0, so we allow n to be 0. So Cn x raised by n, right? So n goes from 0 to infinity. So we have a C naught, the first term, which is a constant, which is just a number, plus C1x plus C2x squared plus blah, blah, blah. Looks like a polynomial functions, right? But this one, polynomial function is polynomial function of degree n. We have a leading term. We have finite many terms for leading term. But with a power series, we do not have a leading term. There's no leading term. The terms keeps going. So this is infinite. infinite polynomial. So here x is a variable and all the coefficients cn, like c0, c1, c2 are just some numbers. So we call this power series. The series like 1 plus x squared plus so on and so forth, it can be written as x raised by n, and n goes from 0 to infinity. So this is called the power series. And of course, in this power series, so C0, C1, C2, any of them might be 0, right? The coefficient might be 0. So maybe you'll only see x term, x cube term, x raised by cube, x raised by 5, or so on and so forth. So this series is a geometric series, right, with a ratio of x. With a ratio of x. Well, if x is less than 1, if absolute value of x is less than 1, we know it converges, right, because it's a geometric series. And if x is greater than or equal to 1, the series diverges. Okay. So this is new today. Right? This is just an example. So the standard form of power series looks like this. Any of the c term can be 0. Okay, definition. A series of the form, this form, 6.1, is a power series centered at x equals to 0. Okay, centered at x equals to 0 only means this, comparing to this, right? So this is a series, a power series. So we have the c term, right? Cn, c term represents some real numbers, and x minus a raised by n. So this is centered at x equals to 8. So this is called a power series centered at x equals to 8. So this one, of course, centered at x equals 0. Okay, so this is new. So let's try to understand the notation. What this is a power series centered at 8. This is a power series centered at 0. Okay, just definitions. Just definitions. Anyone has any questions? To make this definition precise, we stipulate that x raised by 0 equals 1, of course, right? And x minus a raised by 0 equals 1, even when x equals 0 and x equals a respectively. So the series x raised by n divided by n factorial. If we write a couple of terms, the first term is 1, second term is x, third term x squared divided by 2 factorial, then x cubed divided by 3 factorial, so on and so forth. Right. And this series, we could see, you know, we have x raised by 0, x raised by 1, x raised by 2, x raised by 3, so on and so forth. So it's a polynomial series. And now it's a power series. And this one will have n factorial x raised by n. Well, n factorial is just cn term. Right? If we write a couple of terms, we have 1 plus x plus 2 factorial x squared plus 3 factorial x cubed, so on and so forth. It is also power series. And those two power series centered at 0. The first one, Cn's are 1 over n factorial. The second one, Cn's are n factorial. Well, let's see this one. This one, what's the coefficient? What's Cn? Cn is 1 over n plus 1, 3 raised by n, right? That's Cn. And then the x term will have x minus 2 raised by n. So this is power series centered at 2, with Cn equals to 1 over n plus 1 multiplied 3 raised by n. We can also write, it's always good to write a couple of terms, to get a little bit of intuition. So n equals 0, get a 1. N equals 1, we have x minus 2 divided by 2 times 3. Then n equals 2, get x minus 2 squared divided by 3 times 3 squared, so on and so forth. Okay. So we see x minus 2 raised by 0 for the first term. Then x minus 1, x minus 2 raised by 1, x minus 2 raised by 2, x minus 2 raised by 3, so on and so forth. And the other numbers is just Cn, or C0, C1, C2, C3. So this is a power series centered at 2. Okay, convergence of a power series. Since the terms in the power series involve a variable x, the series may converge for certain values of x and diverge for other values of x. For a power series centered at x equals a, the value of the series at x equals a is given by C0, of course, right? Because if x equals a, think about this example. If x equals 2, 2 minus 2 becomes 0. So all the terms involve x minus 2 become 0. So I'm left with the first term, C0. For this, in this case, just 1. Similarly for this one, right? If x equals 0, this is centered at 0. If x equals 0, all the terms involves x becomes 0. So only left with a constant term. So for power series centered at x equals a, the value of the series at a is given by C0, the constant term. Therefore, a power series always converges at its center, of course. It just gets a number, you get the whole series, just get a constant number. So a power series always converges at its center. Some power series converge only at the value of x. Most power series, however, converge for more than one value of x. In that case, the power series either converges for all real numbers or converges for all x in a finite interval. The geometric series x raised by n converge for all x in the interval from -1 to 1, but not including -1 and 1. Right? Because x, the absolute value of x is less than 1. And we can write in the interval notation is open parentheses -1 up to +1 close parentheses, which means not including the boundary points -1 and 1. But diverges for all x outside the interval. Okay, theorem. Convergence of a power series. So a standard form of power series, Cn x minus a raised by n. So the series satisfies exactly one of the following properties, 3 properties. First one, the series converges at the center and diverges for all x not equal to a, okay, not the center. Second, the series converges for all real numbers of x. 3, there exists a real number r, capital letter R, greater than positive, exists a positive real number, such that the series converges if x minus a, absolute value of it, is less than capital letter R, and diverges if its absolute value is greater than R. And at the value of x, where x minus a equals R, the series may converge or may diverge. So inconclusive. Inconclusive. All right, so we have these 3 situations. All right, so consider the standard form of a power series. All right. So Cn is the coefficient, x minus a raised by n. And A is called the center of convergence. So the first one is saying the series converges at its center and diverges anywhere else. Right. Second situation, the series converges for all real numbers. Third, there exists such finite number, positive number, and x minus a, absolute value of it, less than number, so which means this is bounded. Right, this is bounded. Think about x in geometric series, we have absolute value of x less than 1. Right, in that case, r equals to 1. In that case, it's x minus 0 less than 1. But in general, we write as absolute value of x minus a less than r, less than such a number, a finite number. And it converges in this and diverges if absolute value of x minus a greater than a finite number. And then you can imagine, because in this series we have x minus a raised by n, right? N goes from 0 to infinity. If each term is greater than a certain number, so the terms get bigger, bigger, and bigger. If it equals to r, the series is inconclusive. All right, we're going to skip the proof. We're going to see some examples. Let's see this definition. Consider the power series, the set of real numbers x, where series converges is the interval of convergency. And the capital letter R is called the radius of convergence. Okay, if there exists such R, capital letter R, positive, absolute value of x minus a less than R, okay, it converges, then R is called the radius of convergency. But if it's greater than R, it's a series diverges. So if the series converges only at the center, we see the radius of convergence is 0. So if it only converges at its center, so radius of convergence is 0. That means, it only converges at 1 point. So that's no radius, right? Radius is 0. If the series converges for all real numbers, we see that radius of convergence is infinity, right? So because it converges at any real number. So these are some definitions, right? So we have to, so this is new to us, the radius of convergence. So if we do have absolute value of x minus a less than r, and this r we call radius of convergence. Okay, this is talk about our different situations, right? So this is the convergence only at the center. So the radius of convergence is 0 because anywhere else it diverges, right? Converges all real numbers, so everywhere. Or converges in the interval, a minus r, a plus r. So the radius of convergence is r, right? Because from from a minus r to a, that's r. From a to a plus r, that's r. So we call this radius of convergence. Radius of convergence is r. So here radius of convergence is 0, only converges at its center. Here converges at all real numbers, so the radius of convergence is infinity. So if that is such r, so radius of convergence is r. Let's see an example. So we want to find the interval and the radius of convergence. Okay, so we have a, b, c, 3. So we were told to find, so that means, okay, so the first one is x raised by n divided by n factorial. Second one is n factorial x raised by n. The third one is x minus 2 raised by n divided by n plus 1 times 3 raised by n. We see these 3 examples before, right? So first one, to check for convergence, apply the ratio test. Remember the ratio test? Ratio test, we compare n plus 1 time. We divide n plus 1 time with n plus 1 term with n term. So we take a limit of the ratio, absolute value of it. So x raised by n plus 1 divided by n plus 1 factorial. Then, so this is the n plus 1 term. Then divided by n term, which is x raised by n divided by n factorial. We'll do the calculation. We'll do the calculation. X raised by n plus 1, it says x raised by n times x. If I simplify with x raised by n, we get x in the numerator. N factorial divided by n plus 1 times n factorial. Well, n factorial divided by n factorial. N plus 1 factorial can be written as n plus 1 times n factorial. Then n factorial cancel n factorial, so we have 1 over n plus 1. So after simplification, we get x over n plus 1. Right? Now, limit of n goes to infinity of this ratio, x over n plus 1. Right? X has nothing to do with n. So we can pull absolute value of x outside the limit, because the limit only considers n, right, when n approaches infinity. So limit of 1 over n plus 1 when n goes to infinity is what? It's 0. 0 times anything would be 0, right? So get limit, so this limit of the ratio equals 0, which is less than 1. So for all values of x, right, doesn't matter what x is, as long as x is a finite number. Right? X is a finite number. And the limit is 0. So therefore, the series converges for all real numbers x. The interval of convergence is from negative infinity up to positive infinity. And the radius of convergence is infinity. Remember before, when we use the ratio test, right? So here we use the ratio test for this, for power series. So when the ratio equals 0, that means the series of convergence is all real numbers. And the radius of convergence is infinity. Anyone has any questions? So just new terms, right? Just new terms. So we want to find the interval of convergence or the radius of convergence. So what do? With A, we can take a ratio test. Ratio test is take the limit, let n approach to infinity. Absolute value of the ratio, the numerator is n plus 1 term, the denominator is n term. Then after the calculation, right, because the limit only considers n, so we can pull x term outside the limit. Then we have limit of 1 over n plus 1. When n approaches infinity, that's 0. Well, 0 times anything would be 0. So if we get 0, we say all, so of course for all x value, right? For all x value, doesn't matter what x is, as long as x is a finite number. So therefore the series converges for all real numbers. And the interval of convergence is from negative infinity up to positive infinity. And the radius of convergence is infinity. Any questions? Okay, let's see B. B will have n factorial x raised by n. So we'll apply ratio test. So n plus 1 factorial x raised by n plus 1. So that's the n plus 1 term. Divided by n factorial x raised by n term. Right, after simplification, we have n plus 1 times x. Again, we can put x up front. So take a limit n approaching infinity of n plus 1. Well, limit of n plus 1 when n approaches infinity, it goes to infinity. Infinity times any finite number will be infinity. So this is saying the series diverges except its center, right? Because if it's at its center, it just equals to the constant term. So the series diverges for all x not 0. Because 0 is the center of convergence for this, right? Because it's x minus a raised by n. Here we only have x raised by n. That means a equals 0. So this series does converge when x equals 0. When x equals 0, the whole series equals 0 factorial, which is 1. Which is 1. So it does converge at 0. But other than that, it diverges. So it diverges for all non-zero values. Okay, any questions for the second one? The simplification part. A or B? Maybe let's do both. So yeah, it's all algebra. It's all algebra. Let's see B. So we have the numerator, we have n plus 1 factorial. Remember, let me type in the chat. So n plus 1 factorial equals to n plus 1 times n factorial, right? So then when we divide by n factorial divided by n factorial equals 1. So I'm left with n plus 1. Then, of course, x raised by n plus 1, we can write as x raised by n times x, right? Then x raised by n divided by x raised by n, that equals 1. So I'm left with x. Does it make sense? Okay. Can you quickly go over how we know what the value of series is centered at again? Oh, okay. Okay, let's try to remember the power series standard form like this. All right. So Cn times x minus a raised by n. So this is the standard form for power series. So Cn, Cn means we have C0, C1, C2, right? X minus a raised by n means we have x. So if we write a couple of terms of this, we would get C0, right, plus C1, x minus 1, x minus a. Let me write in the chat. So this series, we would have C naught plus C1 times x minus a plus C2 x minus a squared plus C3 times x minus a cube plus so on and so forth. Right? I just read out 3 terms. Okay. So C naught, so C underscore 0 usually is read as C naught, N-A-U-G-H-T. Okay, so C naught. And A is called the center of convergence. So A is the center of convergence. Why is that? Think about x equals A. So when x equals to A, the whole series just equals to C naught, the first term. Because A minus A becomes 0. All the ones with x minus a becomes 0. So only left with the C naught. So a series always converges a power series. Always converges at its center. It's just some new terms. The power series always converges at its center. And it converges to C naught. Right? Because only C naught survive. All the x minus a's become 0. So this is center convergence. And with this one, okay, so let's review those 3 conditions too also. So a power series always converges at its center. Okay, 3 situations. It may only converge at its center and diverges anywhere else. Or it may converge at all real numbers. Or it may converge at an interval and diverges anywhere else. 3 situations. But at least it converges at its center. It converges to C naught, converges to its constant term. All right. Okay. Any other questions? Should we go for C? So C is x minus 2 raised by n divided by n plus 1, 3 raised by n. Okay, A center at 0, B center at 0, or C center at 2. Right? So the center of convergence for C is 2. So we'll apply ratio test again. So limit of n plus 1 term, which is x minus 2 raised by n plus 1, divided by n plus 1 plus 1, where n plus 2 comes from n plus 1 plus 1. Then 3 raised by n plus 1, then divided by the nth term. Divided by the nth term, right? So x minus 2 raised by n plus 1 can be written as x minus 2 raised by n, then multiplied by x minus 2. Then x minus 2 raised by n divided by x minus 2 raised by n, that becomes 1. So we have x minus 2 survive in the numerator. Then we have n plus 1. We have n plus 1 plus 1, that's n plus 2. Then 3 raised by n plus 1. Well, 3 raised by n plus 1 can be written as 3 times 3 raised by n. Then it cancels with the numerator 3 raised by n. So n plus 2 survive in the denominator, and 3 survive in the denominator. And now we have n plus 1 from here, survive from the numerator. So the numerator we have x minus 2 times n plus 1 divided by 3 times n plus 2. Now x minus 2 has nothing to do with n, so we can factor out x minus 2. Then we'll take a limit of n plus 1 divided by 3n plus 2. Well, limit of that by ignore rule, it's just 1/3. Right? Limit of n plus 1 divided by 3n plus 2, we just take the leading term. The leading term in the numerator is n, in the denominator is 3n. n divided by 3n, that's 1/3. So limit equals 1/3. Then multiply by absolute value of x minus 2. Okay. So we have 1/3 of x minus 1/3 of absolute value of x minus 2. And we want the row less than 1, because in the ratio test, right, row has to be less than 1 to converge. So if row less than 1, that means x minus 2, absolute value of x minus 2 divided by 3 less than 1. That means absolute value of x minus 2 less than 3. Right? So you see this 3, what's this 3? That's a big capital letter R, before we were talking about. Right? So x minus 2 absolute value less than 3 implies that x minus 2 greater than negative 3, but less than 3. Then we add 2 for negative 3 and positive 3. So we get x equals to negative 1, x greater than negative 1, but less than 5. So do you see the interval of convergence? So the interval of convergence is a negative 1, right, open parentheses, negative 1, comma, 5, close parentheses. So the series converges from negative 1 to 5, but it diverges anywhere else. Right? Diverges if x less than negative 1 or x greater than 5. Right? The ratio test is inconclusive if the limit equals to 1. And the limit equals 1 if and only if x equals negative 1 or x equals 5. Right? And we need to test these values of x separately. So for x equals negative 1, the series becomes negative 1 raised by n over n plus 1. And look at this. This is less than harmonic series. Oh, this actually is exactly alternating harmonic series because we're starting from 0, because n starts from 0. Right? So the first term is 1. Second term is negative half. So it's alternating harmonic series. And we know alternating harmonic series converges conditionally because its absolute value is harmonic series, which diverges. So alternating series converges conditionally. So at x equals negative 1, it converges. For x equals 5, We do the calculation, we get 1 over n plus 1. Where did that series come from? From simplifying. Okay, at x equals to -1, right? So we have those two boundary points, -1 and 5, inconclusive. So x equals to -1, we just plug in to this series. X equals to -1, -1 minus 2, -3, right? -3 raised by n. Then the bottom is n plus 1 times 3 raised by n. You see that negative 3 raised by n is -1 raised by n times 3 raised by n. So 3 raised by n divided by 3 raised by n, that becomes 1. So we're left with -1 raised by n divided by n plus 1. Okay, so that series just comes from plug in x equals to -1. Okay, so when we get alternating harmonic series converges conditionally. So we know the series converges at x equals to -1. Now similarly, let's try 5. So for x equals to 5, we also plug into the original one. So x equals to 5. 5 minus 2, that's 3. 3 raised by n. Well, 3 raised by n divided by 3 raised by n becomes 1. So the series becomes 1 over n plus 1. So the series at x equals to 5, the series becomes 1 over n plus 1. That's exactly harmonic series. So we know harmonic series diverges. So the series diverges at x equals to 5. So we conclude the interval of convergence is bracket -1 because it does converge at -1. So we're including -1 by using bracket. So bracket -1, comma 5. At 5 diverges, so not including 5, we use close parenthesis. And the radius of convergence is 3, right? Because of this. Because x minus 2, absolute value of x minus 2 less than 3. So 3 is the capital letter R. It's the radius of convergence. Okay, any questions? So this one is a lot. Let's go back. So let's go back. So again, we apply ratio test. So we apply ratio test. So the limit, what's the limit? The limit is a function. The limit is absolute value of function, right? We use the ratio test, saying we need this one to be less than 1. If this one is less than 1, the series converges, right? So we write down this whole thing less than 1. So absolute value of x minus 2 divided by 3 less than 1. Then we multiply 3 on both sides. So we get absolute value x minus 2 less than 3. Right? Now, absolute value of x minus 2 less than 3 implies that x minus 2 is greater than -3, but less than 3. So we add 2 on both sides. That becomes x is greater than -1, but less than 5. So this is saying the series converges in this interval from -1 to 5, but not including -1, not including 5. So what happens at -1 and 5? So we try. We just plug in the value for x. Plug in -1 for x. The series becomes alternating harmonic series. And we know it converges. So that means the series converges at -1 and up to 5. Well, now let's check 5. when x equals 5, the series becomes 1 over n plus 1 because n starts from 0, so this is a harmonic series. And we know harmonic series diverges. So 5, at point 5, the series diverges. So conclusion is the series converges at -1 and from -1 up to 5, but not including 5. And the radius of convergence is 3, r equals to 3. Anyone has any questions? All right, okay. Everyone try this. Find the interval of convergence and the radius of convergence for this series, x raised by n divided by n square root of n. All right, so you try this one. Let me take attendance. I think it's always the same amount of people. Okay. Okay. Okay, Goldman says, okay, absolute value of x less than 1, the radius of convergence is r equals 1. Yes. And what about the interval? About the interval of convergence? Because we need to find interval and the radius of convergence. Interval -1 up to 1. Yeah. Well, did we check? Okay, Paul checked at the -1. At the -1, we get the -1 raised by n divided by square root of n, where that's alternating series. Yeah, radius of convergence is 1. So if it's a positive 1, so -1, we got negative. -1, we got alternating series. -1 to 1, yes. Just, okay, to be exact, because some of you didn't put an interval notation, right? If you only write -1, comma 1, that's just 2 points. That means x equals -1 and 1. So we need an interval notation, like Paul wrote. Right? Paul wrote like bracket -1, comma 1, close parentheses. Okay, let's go over it. Yeah, let's go over this. So n goes from 1 up to infinity. You see, this one n goes from 1. It cannot be go from 0 because we have square root of n in the denominator. Oops. X raised by n. Right. So we'll take a limit. We said n goes to infinity. So n plus 1 term, is x raised by n plus 1 divided by square root of n plus 1 over x raised by n divided by square root of n. Well, x raised by n plus 1, I can write as x raised by n times x, right? Then divided by x raised by n over square root of n, I can do multiply by its inverse, right? So x raised by n divided by x raised by n becomes 1. So I have x, so this becomes, so limit, I have x, oh, I forgot the absolute value. All I have to do is just absolute value of the x term, right? I could do this. Everything, inside the absolute value. So I just have to, so I'm left only with x. So I just have to put absolute value around x, because the n term is positive, right? So that's my variable term. What about the n term? I have square root of n, square root of n divided by square root of n plus 1. So when I take a limit, absolute value of x has nothing to do with n because the limit is in terms of n. I can pull this absolute value of x outside. Then I just take a limit of this term, square root of n over square root of n plus 1. Well, that just equals 1, right? So the whole limit equals 1 by ignore rule. So absolute value of x times 1, just absolute value of x. Well, by ratio test, right? If this is less than 1, the series converges. So you see R, the radius of convergence is equals to 1. Right? The center, so this series converges at the center, right? What's the radius of convergence? What's the interval? So interval goes from -1 up to 1. Open parentheses and close parentheses, right? Because what does this mean? Because this means this. This means x is greater than -1, but less than +1. So writing in the interval notation, there's open parentheses, -1, comma 1, close parentheses. Now, what about at x equals -1? So let's check the boundary points. What happens when x equals -1 and x equals to 1? At x equals -1, we get summation -1 raised by n over square root of n, right? So get this alternating series. Get this alternating series. We can use comparison, limit comparison test. The limit comparison test will give us 1. Give us what we can compare. Oh no, we can use ratio test. We can use ratio test again, right? Ratio test again, we get a 1. So this one converges. So what about at x equals 1? At x equals 1, we get a p series. And this p series with p equals to half. Or half is less than 1. But for p series, it converges when p greater than 1. So less than 1, so half is less than 1, it diverges. So the interval of convergence we can change to be this, right? Ali, is that okay? Okay. All right. Okay, pretty good. Okay, representing functions as power series. So being able to represent a function by an infinite polynomial is a powerful tool, right? Polynomial functions are the easiest function to analyze, since they only involve the basic arithmetic operations for addition, subtraction, multiplication, and division. If we can represent a complicated function by an infinite polynomial, we can use the polynomial representation to differentiate or integrate. Okay, you see, this is the powerful part. Okay, consider a very complicated function. If we can represent it with a power series, and we can differentiate term by term, we can integrate term by term. So in addition, we can use a truncated. It means we cut off the tail. We can use a truncated version of the polynomial expression to approximate values of the function. So the question is, when can we represent a function by a power series? So consider this geometric series. Right, this looks like this, a plus AR, the geometric series. If the ratio, absolute value of the ratio is less than 1, we know it converges. And it converges to the first term divided by 1 minus the ratio. So therefore, if absolute value of x less than 1, the series converges to 1 over 1 minus x. And we can write this infinite series equals to a rational function. You see how powerful this is? Of course, this is for absolute value of x less than 1, right? So this is very powerful. Again, it brings an infinite world, right, to one term. So infinite many terms can be represented by one term, by a function, by a rational function. Of course, for absolute value of x less than 1. So as a result, we are able to represent the function f of x equals 1 over 1 minus x by the power series of 1 plus x squared, when absolute value of x less than 1. We now show graphically how this series provides a representation for the function f of x equals 1 over 1 minus x by comparing the graph of f with the graphs of several of the partial sums of this infinite series. So we want to sketch the graph. We know exactly how to graph this, right? This is a transformation of the reference graph of 1 over x and the graph of considering the partial sums. So f of x equals 1 over x, we get this graph. And if we do 2 partial sums, we get this graph. 4, 6. We see as we do more and more, it's getting closer and closer to 1 over 1 minus x. All right, let's see this one. Okay, any questions for this? Actually, from this. So this is for geometric series, right? So this is a geometric series. And the ratio in this geometric series, the ratio is x. So ratio R just x. Now let's see this practice. So here we get 1 over 1 minus x squared. So they want us to sketch a graph. And the corresponding term. Let's skip this. We don't need to do this. Representing a function with a power series. Use a power series to represent each of the function f. Find the interval of convergence. So f of x equals to 1 over 1 plus x cubed. Well, this looks like a geometric series, right? So we can write as 1 over 1 minus negative x cubed. That means our r equals to x cubed. Negative x cubed.
Can you say again?
Which one?
Oh, what did you say? Like you could rewrite it as what?
Oh, 1 minus 1 over 1 minus negative x cubed. Let me write in the chat. Oh yeah, Paul already wrote. Because plus can be written as minus negative. Yeah, okay. So that means the ratio R equals to, so we recognize it's a geometric series. With ratios with R equals to negative x cubed, right? Because we have 1 over 1 minus x cubed. And also the first term in the series is 1. Right, so we recognize this. Recognize A equals to 1 and R equals to negative x cubed. So that means we can write as 1 plus negative x cubed raised by 1 plus negative x cubed raised by square, and so on and so forth. So 1 over 1 plus x cubed, we write as 1 over 1 minus negative x cubed. And of course, that requires negative x cubed less than 1, because R in this case is negative x cubed. And the A first term is just 1. So A is 1, and R is negative x cubed. So that means absolute value of negative x cubed needs to be less than 1 for it converge. And the 1 over 1 minus negative x cubed can be written as infinite series with negative x cubed raised by n, starting with n equals 0. because when n equals 0, anything raised by 0 would be 1, because our first term is 1. Because our first term is 1. You see this in the numerator? That's 1. That means our first term is 1. So we need to start with 0, because anything raised by 0 would be 1. So second term would be negative x cubed. Right? So when n equals 1, we get negative x cubed. When n equals 2, we get x raised by 6. So on and so forth. So absolute value of negative x cubed less than 1 means x cubed less than 1 means x, absolute value of x less than 1 means the interval of convergence is a negative 1 to 1. Right? And radius of convergence is 1. So then we just write the conclusion. We write, okay, 1 over 1 plus x cubed can be represented as an infinite power series as 1 minus x cubed plus x raised by 6 minus x raised by 9, so on and so forth, for absolute value of x less than 1. Isn't this powerful? Huh? Any questions? Okay, let's see B. So B is x squared over 4 minus x squared. How do we do? Because we need to have the form a over 1 minus r, right? So we want to be able to write in this form. So how do we change that? So, okay, we recognize, how do we write x squared over 4 minus x squared? So in the form of a divided by 1 minus r. So thinking x squared divided by 4 minus x squared equals a divided by 1 minus r. Then we can recognize a, we can recognize r. Well, we see the denominator is 4 minus x squared. So what do we do? Let's factor out 4. So we write as x squared divided by 4 times 1 minus x squared divided by 4. So we factor out 4. Right? We can think this is like a quarter, right? Quarter, or maybe x squared over 4 as one term, as our numerator. Then the denominator divided by now, the denominator will have 1 minus x squared over 4. X squared over 4. Okay, so now we can recognize a equals to x squared divided by 4, and r equals to x squared divided by 4. Right? Because now it's in a divided by 1 minus r. We need a 1. We need a 1 minus r in the denominator. So we need a 1. So that's why we factor out 4 in the denominator. So we put divided by 4 for the numerator. So numerator will get x squared divided by 4. And the denominator we write as 1 minus x squared divided by 4. Does this make sense? Okay, anyone has any questions? Now we can write, right? Now we see, okay, our R is x squared over 4, which is, so absolute value of x squared over 4 has to be, okay, less than 1, right? So x squared divided by 4, that's our R, has to be less than 1. That means x, so we can, so what can we do? We have to do absolute value of x divided by 2. We can square root on both sides, less than 1, right? Then that means absolute value of x less than 2, right? Okay, so we see radius of convergence is 2, and the interval of convergence is -2 and 2, right? And then what about x equals to -2 and 2? So what about x equals to -2 and 2? So we can check that. So radius of convergence is 2. The interval, or all we have to find the interval of convergence. The interval of convergence is -2 and 2. Oh, how do we write it? So we write as x squared over 4 minus x squared equals to, well, our first term is x squared divided by 4. And our ratio also equals to that. So we better start from 1. So summation sign, let me use S, all right, S. So start with n equals to 1, right? Of course, up to the up one is infinity, right? So we have x squared divided by 4, right? Because we start, n starts with 1, raised by n. Raised by n. In this case, so we start with n equals 1. So in this case, our first term is x squared divided by 4 raised by 1. So we get our first term. And our ratio is x squared over 4. All right. So S is just a summation sign. All right. So summation sign, n equals to 1 up to infinity, and x squared over 4 raised by n. Right. If we want, we can write out a couple of terms. So we write x squared over 4 minus x squared equals to, well, the first term is x squared divided by 4, and second term is x raised by 4 raised by 16, right? So on and so forth. Keep going. Just write out 2 terms. You could keep going. You could write x raised by 6, right? Over 64. Right. Okay, anyone has any questions? Any questions? So with this, we see these 2 examples. Okay, we see both A, B examples. It's just a geometric series, right? We just use geometric series. We just have to manufacture A, manufacture R. Well, let's see more examples. Oh, it's here, right? So we x squared divided by 4 minus x squared, factor of 4, because we need 1 minus r. So factor of 4, get 1 minus x squared over 4. Then this x squared over 4, we can put it in the numerator. Right? X squared over 4, just our a term, first term a. Then the bottom will have 1 minus x squared over 4. So x squared over 4 over 1 minus x over 2 squared. Okay, they did more complicated. They did more complicated. So mine works, and this one also works. This one is saying, okay, but I don't like this one, because remember, we want to manufacture A, so we want to follow A over 1 minus R. We want to manufacture A, we want to manufacture R. All right, I don't like this one. Okay, everyone try 6.3. All right, this one is a little tricky because you see x cubed, the 2 minus x. All right, let's try this one. Let's get some water. Just remember to manufacture A and manufacture R, okay? Okay. Negative 2 to 2. Radius of divergence equals 2. Okay. So how do we write in a power series? So we want to represent with a power series. What's A? What's R? Oh, Golem, you want to see radius of divergence. We use capital letter R, because here we have A. Because we want to use A divided by 1 minus R, right? So we need to find out A. We need to find out R. And then we form our geometric series. So x cubed 2 minus x. Let's go to the whiteboard. Oops. X raised by n plus 3 over 2 raised by n plus 1. Looks great. Looks great. Right, looks great. Okay, so let's see. Let me write. So we have function x cubed divided by 2 minus x. Well, the wind is blowing hard. So let's figure out, so we want to be able to manufacture A, manufacture R. So we want to be able to write in this form. So how do we do that? First, we want to factor out 2, right, in the denominator. If we want to factor out 2, we write as 1 minus x over 2. Right, for the denominator. Then these 2, we will probably want to write with here. So x cubed divided by 2. Now we see we have A equals to x cubed divided by 2. Our R equals to x over 2. Right? And of course, we want our R, which is x over 2, less than 1. Right? This less than 1, we can represent this function in, well, we have to consider our first term. Right? Our first term is x cubed divided by 2, our first term. Then multiply by our R. Our R is x over 2. Well, with, let's see, this is with n, right? And n, we want to start with 0 up to infinity, right? So we need to figure out, right? So we have this rational function. For rational function, right, we say, okay, converges to, so geometric series converges to A over 1 minus R. A is the first term, R is the ratio. So we go through this process. We basically manufacture A equals x cubed divided by 2, R equals x over 2. Multiply both sides by 2. Okay, so we can simplify this. I think Golem is suggesting us to simplify this, right? So once we have A, once we have R, we can write in the summation. So A is our first term, right? And this ratio part, the first term we want to be 1, so that means n, we want to start with 0. Anything raised by 0 will be 1. So 1 times this one, we get our first term is x cubed divided by 2. Now maybe you can simplify this a little bit. So simplify a little bit. I'm not going to rewrite it. Let me just rewrite it. So n equals 0, starting from 0, infinity. So now we see we have x raised by n times x raised by 3. That's x raised by n plus 3. That's what Golomb has in his formula. Right? We have 2 times 2 raised by n in the denominator. That's 2 raised by n plus 1. And then with this condition, absolute value of x less than 2. That's it. So we see this one. So we write this x cubed divided by 2 minus x. Okay. So the rational function x cubed divided by 2 minus x can be represented as an infinite series with x raised by n plus 3 divided by 2 raised by n plus 1, starting from n equals 0 up to infinity, with absolute value of x less than 2. Okay, so this should be our answer. Or if we want to write the interval, we will write as -2 up to 2. So radius of interval is this. Radius of convergence is 2, and the interval of convergence is -2 up to 2. Great. Right. So Golomb's and mine are exactly the same, right? X raised by n plus 3 divided by 2 raised by n plus 1. Yes. Just with the condition of absolute value of x less than 2, or with the radius of convergence, with the interval of convergence of -2 to 2. Okay, anyone has any questions? Okay, if not, I guess I think that's it for today. Let's go back to the textbook. I think that's it for today. So today we learned power series. Power series, and some functions can be represented with a power series with certain conditions, especially for rational functions, which is a power for 2. So next week, next Monday, we're going to talk about property of power series, and then next Thursday we're going to talk about very important series, Taylor series and the Maclaurin series. Monday or Tuesday? I'm sorry, Tuesday. I have other 2 classes at Monday. So I teach Monday, Thursday for 2 classes, and Tuesday and Thursday for this class. Sorry. So Zachariah is asking, so the first term is always the numerator after getting 1 minus r in the denominator, right? Yes, because we have a divided by. So the form for geometric series, it converges at a divided by 1 minus r. So the one in the numerator is the first term. So a is the first term. R is a ratio. Does that answer your question? Okay. All right. Okay, so I will assign homework. And if you have no questions, have a good night then. Okay, have a good weekend. Good night. Good night. Have a good weekend. Good night.